access the lab content in the content area for lab number 10, resistors in series and parallel. And you can access the lab instructions by clicking on the first link, and that will take you to this PDF document. And for those of you who have tablets, you can download this on your tablet. And as you complete the report, you can actually write in your answers in the spaces provided. If you don't have a tablet or PDF editor, which is also, I think, the Microsoft Edge browser offers editing of PDF documents. You can also do that in the browser, but you could also copy this into a Word document and then type your answers, copy and paste whatever you need to add into a report. And then in the end, convert it to a PDF document. So that's the lab worksheet and instructions. And for the simulation window, you can access, we're going to use the lab option for the circuit construction kit. And this is how the simulation window looks like. And I'm going to turn on the schematic view. You have the real life view and the schematic view. So in the schematic view, you don't see the real life pictures of the object, but you see the symbol that are used in electrical circuits. And to the right, you need to check all these boxes, show values, labels, and current, and of course, electron current. And at any point, you can reset your window by clicking on the reset button at the lower right corner. So back to the instructions. Now that we've accessed the simulation window, we've set up the controls. Of course, you have your voltmeter and ammeter. The first two activities includes, basically, this is like an exercise. So given 3 resistors, each with a value of 3 ohms and a 9-volt battery, you asked to figure out how you would wire these resistors to produce 1 ampere of current. And the hint is to think of Ohm's law and what equivalent resistance would be needed. So the voltage is 9, the current that is expected is 1. What must the resistance be? If you go to Ohm's law, voltage equals current times resistance. As you can see on the whiteboard, V equals I times R. The voltage is 9 ohms. The current is 1 amp. And it's very straightforward to figure out the value of R that will make this equation consistent. So if V is 9 and I is 1, then I'm sure you can figure out what R must be for you to get 9 volts in this equation. Once you figure out that number, the next question is, how would you combine these resistors to produce the desired current or the desired resistance? And there are 2 options with learning class that you could combine resistors in series or in parallel. And I'm just going to show again here. This is a series circuit with 4 resistors. Series, this is how you wire resistors in series. And this is how you wire resistors in parallel. So the resistors kind of are kind of parallel to each other. All the love terminals of the resistors are connected to the same point, same potential, and the right end similarly. So these are hints or guides to help you figure out how to combine your resistors. So once you've figured that out, you draw the diagram showing that this is how I will wire these 3 resistors with the battery to get 1 amp. And then you're going to build that actual circuit using the simulation window and then test it using the ammeter to see if the current in your circuit is actually 1 amp. And then for step 2, you're going to show the calculation for the equivalent resistance. So if hypothetically you decided that the resistors have to be wired in parallel to give you 1 amp, then you will show how you add 3 resistors in parallel to obtain your equivalent resistance. And then once you have the equivalent resistance, again, show how you calculate current using Ohm's law. So you know voltage is 9, you calculated your equivalent resistance, V equals I times R, you can solve for I from that equation. And that is C. That's part C. Now, step 3, for the same combination, 3 resistors, each having a value of 3 ohms, a battery with 9 volts, how would you combine these resistors to produce 9 amperes of current from the battery? Again, think of Ohm's law and what equivalent resistance would be needed. So in the equation, V equals to I times R. Now V is 9 volts, I is 9 amps. So 9 multiplied by what will give you 9? The answer is obvious. So once you know how much resistance you need, it's going to tell you how you must wire those 3 resistors. And then you're going to draw the diagram of the configuration here under A, and then under B, show the calculation for the equivalent resistance, and then C, show the calculation for the current. For the next activity, you will analyze the series and the parallel circuit and answer the questions that follow. The questions are to describe the patterns that you see in a series circuit, the patterns you see in a parallel circuit. So basically you have 3 resistors, R1 is 10, R2 is 20, R3 is 30. So R1, just fill in 10, 20, and 30. So that's 10 ohms. And the R2 is 20 and R3 is 30. Same here. So 10, 20, and 30. So that's already given to you, but you would need to wire 10 ohms, 20 ohms, and 30 ohms in series, and then 10 ohms, 20, 30 in parallel, and then use your ammeter and voltmeter to measure the currents and the voltages, and just fill up these 2 tables. And then you can take a screenshot of your circuits and then paste it here for the series and parallel, or you can just draw the circuit. Okay, then the next activity for a combo circuit, you have 2 combo circuits. Combo simply means you have a slightly more complex pattern, a combination of series and parallel in the same circuit. You're going to set up the circuit as shown, and then again, your R1 is 10, 20, R2 is 20, R3 is 30, and then you measure the currents through R1, through R2, R3, and then the voltages. You do the same for the combo circuit number 2. And then the final, well, not the final, the next activity is about shorts. So you identify the segments or branches in this circuit that have no resistance. And branches that have no resistance are called shorts. And so you're going to predict the effect of the shorts on the circuit and then build the actual circuit and test to see if the shorts have the predicted effects, the ones you predicted. And then next, you study switches. You identify the switches in this circuit, in this diagram, and then write down what is the effect of each switch. What happens when you close the switch or when you open the switch? Then make the circuit using your simulation window, and then actually close or open the switch to see if the switches behave as you predicted. Finally, you're going to identify which batteries in these 2 diagrams are wired in series and which are wired in parallel, and then build the actual circuit and verify the predictions. Which one did you predict to have more current? Which one did you predict to have more resistance? And fill your answers in this table. So now let's go to the simulation window. And here I'm going to show you how to set up the simulation and build any kind of circuit. So let's say, let's start with a series circuit. I'm going to build a circuit with 4 resistors. Of course, your activity requires just 3 resistors, but I'm going to use 4. So these are my 4 resistors. Series, I'm going to join the resistors end to end, and then I'm going to grab a wire here, pull it down, and then I'm going to grab another wire down here, and then a battery right here, and I'll get 2 more wires. And notice that you can stretch the wire out to any length. So now I have 4 resistors wired in series to a 9-volt battery. If I wanted to change the value of this battery, I'll just click on the battery symbol and then slide this along to the desired voltage. Okay, so this is now 45 volts. I can also alter the values of these resistors. I can change this to 5 ohms, 10, and then I'll change this to 15. I'll change this to 20. So I have 5, 10, 15, 20 wired in series with a 45 volt battery. And I deliberately chose different numbers because I don't want you to simply copy what is in the simulation. I wanted to actually build your own circuit with the numbers given in your worksheets, and then have an understanding of how everything works. Now, how do we measure the current? So drag the current meter. This is an ammeter, and then place the scope on the path. You can see this shows us 0.9 amperes of current coming out of the battery. If we check just before the battery, it's the same number. If we go just before the first resistor, we have the same current. After the first resistor, the same current. After the second resistor, the same current, same current, same current. And you can already see the pattern for this series circuit. And that's consistent with what we've learned in class about series circuit. Now, let's measure the voltage. So you place 1 probe on either side of the device you're measuring. And this is 45, which is what we expected because the battery has a value of 45 volts. Now, if I were to measure the voltage across any segment of wire that doesn't have a resistor, obviously we expect the voltage to be 0 because wires don't have any resistance. Therefore, there is no voltage drop across a segment of wire that doesn't have a resistor in between. Even though there's current, but because the resistance is zero, any current multiplied by zero will give you zero. Now let's measure the voltage across the 5 ohms. Clearly, you can see it's 4.5 volts. Now, is this consistent with Ohm's law? Let's check. So the scope, place the scope here. The current going through the 5 ohm resistor is 0.9. What is 0.9 multiplied by 5? Somebody multiply that and tell us the answer.
4.5.
4.5. So that indeed validates Ohm's law for this. Let's go across the 10 ohms. The 10 ohms is 9. Again, the current is 0.9. 0.9 multiplied by 9 is 0.9 multiplied by 10 is 9. Again, that's consistent. Somebody predict the voltage for the 15 ohms. The current is 0.9. What is 0.9 multiplied by 15?
13.5.
Okay, let's see if that's the case. And it's indeed 13.5. And of course, the voltage across 20 will be 18, twice that of 10, because 9.9 multiplied by 20 is 18 volts, as you can see. So that indeed validates what we've learned concerning Ohm's law. Now, if we go across all the resistors, we should get 45, which is 18 plus 13.5 plus 4.5 plus 9. That gives you 45. Okay, so that's a series circuit.
I have a question.
Yes.
Should we, include, wire between each of the resistors, or does it not matter?
It doesn't matter as long as you can join the resistors directly.
Okay.
Yeah, I like it.
Say it again. Was that a comment or a question?
No, my bad. My mic was on. Sorry.
Okay. All right. So so that's a series circuit, and I'm going to clear this up and then construct a parallel circuit. And now for the parallel circuit, you may need to add some wire. And I'm going to use 4 also, but you don't have, your exercise actually asks you to use 3. So, but this is just an illustration. So I'll place my battery right here, and then I can add a wire to either sides. Then you can join this. Now you can actually join this like this. I mean, these are wires. You can literally bend them to any shape you want. Or if you wanted to, you know, remain in a nice geometrical or rectangular shape, you can drag this down and then add a wire here and a wire here. So this now constitutes a parallel circuit with 4 resistors. And if we stick with the same logic, let's say we change the first one to 5, the second one to 10, the next one to 15. Just to see the effect. You know, the current in the other one was 0.9 amps, and the 5, 10, 15, 20, and then the barrier was 45. Okay, here it gives us a warning, the animation speed limit reached. So we're going to reduce the voltage to like 30 volts to stay within the speed of the animation. But you can then test the currents, and you would see that for the same 4 resistors wired in parallel draws more current than the ones wired in series. We had 0.9 for the series combination, and here we have 12.5, which is more than 10 times the value of the series current. Now, but notice that when you check the current going through the resistors branch by branch, you notice that the current is not the same. Whereas in the series, it was the same. So here we have 1.5, 2, we have 3, and then 6. So as you can suspect, because of the varying resistance, the branch with less resistance has more current, followed by this, followed by 15. And as the resistance increases, the current successively decreases. But if you add up 1.5 to 2, that's 3.5, plus 6, plus 3, that's 6.5. Then plus 6, that's 12.5, which is the total current out of the battery. Again, that's consistent with the junction rule we learned, that sum of currents into a junction equals sum of current going out of the junction. What about the voltages? So look at the voltage across the battery. It's 30 volts as expected. How about the voltage across a resistor number? The 20 ohm resistor is 30 volts. How about across the 15 ohms? It's the same. Across the 10 ohms, it's the same. Across the 5 ohms, it's the same. So that's a pattern that you ought to document in your report. Now, if we pick any segment of wire that has no resistor in between, again, you see that the voltage is 0, which is consistent with what we know. Okay, so that's a series. This is a parallel circuit. And then next, I'm going to build a combo circuit. So combo circuit, I can do this like that. And we'll drag a wire here. Add a battery here. So as you can see, this is a combo circuit. You have, if we check values, you can see Again, you can change these values around to have different, values. So the 4 and 8 are parallel to the 10 and 12, which are in series with the 9-volt battery and in series with the 10 ohms. So you have a mixture of series and parallel in the same circuit. 4 and 8 are in series, 10 and 12 are also in series, but the group of 4 and 10 and 10 and 4, 8, 10, 12 are parallel to each other. As before, you can use your meter to measure the current through each device, the current through the 10 ohms, the current through this other resistor, the current out of the battery, the current in the upper branch. Okay, you can measure the voltages, voltage across this tube. Okay, so I have a negative value, so that means I need to reverse my probes, so 3.93, because the positive terminal is this way. So the positive, the red side should be towards the positive terminal. Okay, so this is a combo circuit. And then for the other activity, circuit with switches, I mean, that's really just the same thing we did. So just that now we're going to add a switch. So we said this is my circuit. And then here, I'll add a switch, battery, then close it off. I click on the switch, see the effect of on and off. So I think that covers everything you need to know to be able to complete the simulation. Are there any questions?